All right, we were working in section 3.4 last time, and we had encountered several different types of algorithms. Remember, algorithms are just ways of doing things for both addition and subtraction. And we are at the point where we are looking at addition and subtraction in other bases. And I believe we've done maybe one example. 11? Is that look right? So we're ready to start 12. Okay, so number 11, let me just go back for a second. Number 11 was addition. And we talked about the fact that we can add in our standard algorithm, but we just have to keep in mind the base that we're in so that we don't use digits that don't exist in that base. And then we also did it with scratch addition to remind ourselves what that actually looks like and how we could use that in that system instead. So we're going to do the same kind of thing now on number 12, but we're going to do subtraction. So this is 3, 4 base 8 and 1, 7 base 8. And the first thing we're going to do is we're going to do it with a standard algorithm because that's the one that we feel most comfortable and confident of ourselves in. And we're going to see how that actually looks for maybe for a child who isn't so very comfortable with it by doing it in another base where we're not quite so comfortable. That's the idea. All right, so when we're looking at this, of course, even in base 10, we recognize I can't take 7 away from 4, right? So what do I have to do if I use the standard algorithm? I borrow. All right, so if I'm going to borrow, then the 3 is going to become a what? A 2. Now, when I borrow in base 10, how many do I borrow when I borrow? 10. I take away the 1 and I borrow 10 from the column over. But I borrow 10 because it's base 10. So if I'm in base 8, I'm going to borrow 8. So I've got 8 plus the 4 that are originally there, and 8 plus 4 would be 12. So I'm going to mark out the 4 and I'm going to write down 12. Not 14. Okay? Now, I'm not writing down the 12 in the sense that there's a number 12. Well, there's not a number 14 when I write down 14 in base 10 either. It's a 2-digit numeral, right? Same kind of thing there, okay? But I'm writing down the value that we understand to mean how many if I count them singly. So I have 12, and then I can actually subtract like normal. So when I subtract the 12 minus the 7 in the the right-hand column, what do I get? That's 5. And then I subtract 2 minus 1, I get 1. Yes. And then I need to make sure that I write base 8 down here. Okay? So the condition that you have to remember is when I borrow in another base, I borrow the value of that base. Borrowing base 10, we borrow 10. So borrowing in base 6, we would borrow 6. Okay? All right, let me show you how this would look if we did equal additions, and this will be a good reminder for us as well about equal additions. So we're going to write down that 3, 4 and that 1, 7 again. Do you remember what the key thing is, or if you want, you can look up on the example right before it because it is on this particular page you're on. What's the big deal about equal additions? No borrowing. And we just did an example where we see that if we're going to do this in the standard algorithm, we need borrowing, right? So what we do instead of borrowing with the equal additions is we add something to the second value, the lower value, in this case the 1, 7, so that we won't need to borrow. Now in particular, I'm going to tell you what we're going to borrow and then I'm going to explain why it works. I'm sorry, we're going to add and I'm going to explain why it works. We're going to add a 1 here. Why would 1 be the value that we would need to add? Because it's in base 8, so the 7 will become an 8. And that's too many in one place, right? So it rounds the next value up. When I take 1, 7 and I add 1 to it, I'm basically saying what comes after 1, 7 in base 8? Well, it's actually 2, 0. You get Amanda? You were excited. I see you knew what we were headed to. That's awesome. But if I put the plus 1 on the 1, 7, what else do I need to do? I have to do it to the top, right? I have to put a plus 1 on the 3, 4. Now 3, 4 is easy because the 4 is not anywhere close to 8. So when I take 3, 4 and I add 1, 2, what do I get? 3, 5. And these two subtract just fine with no borrowing. What is 3, 5 minus 2, 0? 1, 5. And again, this is base 8. Okay, any questions on that one? Okay, we're going to try another base. We're going to try base 3 and see how this works. Okay, base 3 has 3 digits because it's base 3. And there's no 3s. It's 0, 1, and 2. That's a reminder for us. So the first thing we're going to do is we're going to do this again in the standard algorithm. This one's an addition problem. 1, 2, 1, 2 plus 1, 1, 2, and it's supposed to be in base 3. Now, if this were base 10, we'd take the 2 and the 2 and we add it to get a 4, right? No problem there. Problem is there's not a 4 in base 3, right? So what do? Well, we recognize it's going to be a 4, and what we can think of is we can think of what in the world is 4 in base 3. That is, how many 3's is it? Plus how many of 1's are left over. So if I have the number 4, how many 3's are in the number 4? There's 1 3. And then how many's left over? 1. So I will have the leftover 1 down here on the top, on the bottom, and I will carry the 1 over because this is the 3's column. I have 1 3 that I'm carrying over. It's like I have 4 items in a pile and I'm grouping it into one group of 3 and what's left. I have one group of 3 that I'm going to carry over to the next column. Think about that concrete model that we did, right? The concrete model had these pictures where these blocks were in order, okay? And I had a long, and my long was whatever the base I was in. So when we were working in last time, our long was 10 long. Well, in this system, our long would be 3 long. So I'd have 3 of these things grouped together that automatically move over into my next column because that's the column that has 3's in it. And I have 1 left over, so that's the one that gets written down underneath the 2 2's. All right, next column, the 3's column. How many do I have in the 3's column? 1, 2, 3, right? You guys see that right there? The three 1's. So I have the number 3 in the 3's column. 1 plus 1 plus 1 is 3. But I don't have a 3 in base 3. So how many 3's is 3? Well, it's 1. So just like when I get to the number 10, I move the 1 over and I have 0 leftover 3's. This just feels weird, right? Okay, so let's do the next one. 1 plus 2 plus 1. We already did that. That's 4. What's that going to give me? It's going to give me a 1, 1. And then I have the 1's column, or the 4th column over where I've got the 2 1's. And 1 plus 1 is going to give me the 2. And this is base 3. All right, so what I'm going to do next is I'm going to show it to you with, and we'll do lattice this time. Do the lattice algorithm. So if you remember, lattice algorithm means that I'm going to have a grid underneath that's going to have the same number of boxes as I have terms in my add-ins. And then I'm going to take each of those and I'm going to split them in half along the diagonal, the bottom left to the top right. And it doesn't matter whether I move left to right or right to left. I'll just move from left to right. And so when I do this, I add the 1, and of course there's nothing right here. There's a 0 right here, so it is just 1, and so 1 goes in the bottom right corner. When I add the 2 plus the 1, I do have to recognize that that's 3, but in base 3, the number 3 is represented as 1, 0. And then I've got the 1 plus 1 in the next column. Well, that's just 2, so that goes in my bottom right corner. And then I have the 2 plus 2, which we've established now. That's 1, 1. So it goes in here like this. With lattice, what we do is we extend along our diagonals. And we will start at the bottom right corner. Often it doesn't matter, but here on this one it does because our numbers get large enough. My bottom right corner is a 1. And then I have 1 plus 2 in the next diagonal, and that's actually 3. But 3 in base 3 is written as what? 1, 0. So I'm going to carry my 1 over here, and I'm going to write a 0 down below down here. So here's that 1 that's been carried, and now I've got a 1 and a 0 in that 3rd column, so that's a 1. And then I've got a 1 and a 1 in the 4th column to the left, and that's a 2. So this is 2, 1, 0, 1, base 3 with lattice. So we did an addition one. Let's do a subtraction one, okay? Any questions on this one before I move on? Okay. Subtraction in base 3. We've got 1, 0, 0, 2 minus 1, 1, 0. It's in base 3. Now, as I start with this one, the right-hand column is good to go. I mean, 2 minus 0, yay, no borrowing required. That's just plain old 2 in whatever base I'm working in. It's a good deal. But of course, the next 2 columns both have problems, right? Because I've got 0 minus 1 in the next 2 columns over. So I have to go over here and borrow. So in this system, when I take this 1 and I turn it into a 0, I'm going to borrow. How many? How many do you borrow in this base? 3. Why is it base 3? Why am I borrowing 3? Because it's base 3. Yeah, that did not come out right at all. So I am borrowing 3 because it's base 3. I do end up writing a 3 down because I don't have anything to add to it. I've got zeros right now as it is, like this 0 right here, right? So I don't have to add anything to it. It really just is 3. The problem is I'm not done there. I need to continue the borrowing to the next column. So this 3 will become a 2, and I borrowed 3. So this is a 3 now as well. And then I can do my subtraction. So moving from right to left, I've got 3 minus 1 now. So 3 minus 1 is 2. And I've got 2 minus 1, which is 1. And then this is base 3. All right, I'm going to do another one with equal additions on this one. All right, so as we talked about before, the ones column is great. I mean, 2 minus 0 is 2, that's fine. But the threes column, the one that's got the 0, 1 right next to the 2, that one I would have to borrow. And so I don't want to have to borrow. That's the whole point of equal additions. I want to add something to this so that I don't borrow. So what do you think I need to add in order to make this work? 2, 0. So Amanda, where did you get 2, 0? That's a very good description. So she's looking at this one right here that is circled in blue. And in order to get that one to turn into a 0, we have to add to it whatever would make it a 3 in our base system, because this is base 3. And a 3 in base 3 turns into a 1, 0. So we want that number to become something different. And so we're going to add 2, 0 to both of these, and let's see where we are after that. So on top, that's really nice. That's 1, 0, 2, 2. And on bottom, of course, there's a 0 still here. This one becomes a 0. And that 2 that's added in that column to the 1 ends up becoming 3, which carries over to the next column. So instead of this now, I actually have 2, 0, 0. Are you guys with me on that one? So what happened was I added the number 2 here, and 2 plus 1 is 3. Can't have a 3. It becomes 1, 0. So that column, that spot right there turned into a 0, and the next column over adds 1 to it. It carries, basically. And that only prolonged my problem, right? Because now I still have the third column from the right, and it has a 0 minus 2 in it, and that's not okay. So what would I need to add to this one in order to get that 2 in the 2, 0, 0 to go away? Good. 1, 0, 0 is correct. You bet. Again, on top, the addition is really nice because that just becomes 1, 1, 2, 2. On bottom, what in the world do we get when we add 1, 0, 0 to the 2, 0, 0 we already have? Right, we get 3 zeros after that 1 that we already have. And then the subtraction involves no borrowing. So I subtract down, I get 2, and a 2, and a 1. So this is 1, 2, 2, base 3. All right, any questions on that? Okay, we're going to shift gears a little bit. We're going to do a little bit of mental math and eventually some estimation, I believe, as well, if I'm remembering right. Mental math, so this is the idea of changing something using properties of algebra, basically, or properties of numbers, to be able to add or subtract something in a more convenient way. Something you can do in your head is the idea. Okay? So take a look at this example. We have 46 plus 38. So the first one says that we're going to add from left to right. This is our method. So what we're going to do is we're going to add the tens digits together first. So we have 40 plus 30, which gives me 70. And then we add the ones digits, 6 plus 8, which gives me 14. And then instead of adding 46 plus 38, we end up adding 70 and 14, which is easier to add than the first two numbers were. That's 84. Now, is it efficient? Not really. I mean, I did 3 additions instead of 1, right? But it's very clean, and it's something that in your head you can do. Now, the catch is, of course, in all of this, when it says mental math, you're going to have to show me your mental math because I can't see inside your head. So you have to show me that you actually did 40 plus 30, and you have to show me that you did the 6 plus the 8, and then you have to show me that you added those two together. So you're just showing me what you're thinking is the idea. Okay? So we end up getting 84 on this one. That one is addition from left to right. So you're adding the leftmost digits together first. The next one, breaking up and bridging. So this one, instead of adding the whole tens digit to the tens digit, what we're going to do is we're going to keep the first number the same, 46, and we're going to add 30 to it. So it's like we're going to ignore the ones digit on the other term. So what's 46 plus 30? 76, And then we're going to add what's left over that we didn't already add to that. So you break it apart. That was great English. You broke it apart, right? You're basically breaking the 38 apart into 30 and 8, and you're bridging by adding them together one at a time. So then 76 plus 8 becomes a one-digit addition to something instead of a two-digit addition, and that would become the same 84 that we had before. Again, it's just another way of doing it in your head that makes it a little bit quicker in your head to do, a little bit cleaner in your head to do. Okay, trading off is the next one. This one is actually a lot like equal additions, except that it's for addition instead of for subtraction, okay? So let's take a look, and I'm going to write it as a vertical problem. So you have 46 plus 38. And the idea is that the 38 is made basically a little bit difficult to add because the 8's so large. I mean, that's the kicker, right? The 8 being as large as it is makes it difficult to add the 6 and the 8 together, potentially. So it would actually be a lot easier if that 38 were a 40. Agree? It'd be easier to add 40 to something than to add 38. But if I add 2 to the bottom term, I'm going to subtract 2 from the top term. And the reason that works is because these are both addition. Okay? So this is kind of you're balancing something. So these two things are added together. So if I add a little bit to this one, I have to take a little bit away from this one so that when I add them together, I get the same result. That's the deal. They're not balancing. It's not a scale like I just threw in the air. But you're just taking a little bit away from one thing and putting it onto something else. And so this ends up being 44 plus 40 by doing that, which is super easy to add together because there's no carrying. And because we got zeros involved, that's nice too. So this one is almost like equal additions, right? Equal additions, you add the number at the top and bottom because it's subtraction. Trading off, you add a little bit to one, take a little bit away from the other one. Okay, is everybody good so far? I covered 3 of them. Okay, compatible numbers is next. Using compatible numbers. Okay, compatible numbers is the idea that some numbers are easier to add together than others are. So in particular, I mean, there's nothing wrong with adding the 40 plus the 30, but then I get 70, and I've got to have the 70 plus the 50. And then if I'm going from left to right, and then I've got to add that value to the 70 plus the 60. It's not real simple to just go in order. There's a simpler way to do this. In particular, what 2 numbers might you like to pair together because their addition is so nice? 60 and 40. Why in the world would you want to do that, Amanda? Because they equal 100. Are there any other numbers that are like that here? 30 and 70. And then I still have the 50 left over in the middle, right? And then the grand result of all this is 250. This is what I do with some estimation when I go grocery shopping and want to make sure that at the end I have enough money for what I'm buying. Is I say, oh, these two add together to be about $5, and these two add together to be about $3.50, and whatever. And I add them together in such a way that I can do it in my head quickly. Okay, I mean, this is exactly the method that I use with some rounding involved because I'm really not caring that I have the exact amount of money. I just want to know I have enough money, right? You don't want to show up at the register and be like, I'm sorry, you can put the fudge bars back. You don't want to do that, okay? So this is compatible numbers. It's just adding the numbers that are nice to add together. All right, here's another one. So what we're moving into on this one is these numbers are not compatible. There's only 2 of them. But we would like to change one of them to make them compatible. So in particular, if I had the number 35, what number would make a nice compatible number to add to 35 that's close to the 68? 65 is what we're probably going for here. Just like on the last slide, the compatible numbers were numbers that added to something that was a whole with lots of zeros. It was 100 in particular, right? So if I took 35, the number that would make that into 100 is 65. But that's, of course, not all I have. I have 3 more than that, right? So in some sense, we're going to take the 68 and we're breaking it apart into 2 numbers, one of which is compatible with what we already have, and the other that's just the leftovers. So these 2, we did it because these 2 are very nicely 100. So the total right here then is 103 for all of it. Okay, next ones are subtraction ones. There's 3 of these. And the first one is breaking up and bridging, which we saw just a minute ago. So breaking up and bridging is the idea of taking the second number and breaking it apart into its components. So like 30 and 8, okay? So what we do with breaking up and bridging is we subtract off the tens value, in this case the 30. So when I do 46 minus 30, what do I get? 16. And then I take that 16 and I subtract off the other value that I didn't already subtract. 16 minus 8 is 8. So you're just doing it in 2 steps. 2 steps that are easier to do because I don't have to do any borrowing with them, or at least not a lot of borrowing. And I end up at the end involved with something that's a single digit that I'm subtracting, which makes it nicer to work with. So that's called breaking up and bridging with subtraction. The next one you've already seen before. It is trading off, but we also had another name for it before. We called it equal additions. So we'll remind you what this is. The idea is no borrowing, right? So what would I have to do so that I don't have to borrow here? Add 2 on the bottom. And with equal additions, or trading off with subtraction, this means I add 2 to the top. Let me do it this way. So this becomes 48 minus 40 for a grand total of 8. This isn't a different method. It's just got another name for us all. And then the last one is not all that really beautiful or anything either, but it is the idea that sometimes we can ignore numbers and then just use them in the end as part of the answer, especially when we're doing mental math, which is the whole point. If I'm looking at 4,600 minus 3,400, do the zeros matter? They really don't, not in terms of what I'm calculating in my head, what I'm doing. So in my head, I'm really thinking, what is 46 minus 34? And what would I get? 12. And of course, 12 is not my answer, right? What's my answer? 1,200. So you drop off the zeros when you're doing the calculation, but then in the answer, you include them back into the answer. All right, the last thing in this section is estimation. We have 5 examples of estimation. Some of them feel a lot like the mental math stuff we did before, but they have this additional property, kind of like when I was describing me in the grocery store, of doing something where we're not going to get an exact answer. So let's take a look. The first one is called front-end estimation with adjustment. Have we talked about front-end estimation in here? No? Okay, I think it was my other class that we were talking about it a little while back. All right, so front-end estimation is the idea of where we only use the very first digits, and that's what we add together. So, in other words, 332, 462, 225, I use the 300, the 400, and the 200, and I add those values together first. So far, so good? So what would I get if I add 300, 400, 200? 900. And then I take the parts that I didn't add, in particular 32, 62, and 25, and I adjust for what's there. So you might think compatible numbers. You want to think, if I add 2 of these together, do I get something nice and friendly or close to something nice and friendly? So in particular on this one, if you take a look at 32 and 62, what is that almost? Yeah, this is almost 100, right? And the point is in approximations, this is approximately 100 when I add those together. We're not dropping the zeros off at the end. You know, I'm not adding 30, 60, 20. That's not what I'm doing. I don't do one more step of the same thing. I take a look at what's left, in this case the tens and the ones place, and I approximate using, in this case, compatible numbers is what I was looking at. Approximately 100 here. This is actually equal to the 25. So now I've got 900, 100, and 25, and I'm going to combine all those pieces to give me an estimation of what? 1,025. 900 and 100 is 1,000, then I've got 25 more. Now, when you do these estimations, sometimes you won't get the same answer as someone else. That doesn't mean that you're both right or you're both wrong. It could mean that you both actually have different things going on that make you equally right or equally wrong for that matter. But you could actually end up with a slightly different estimate based on what you're using as your compatible numbers. Occasionally that will happen. So be careful on these with comparing your answer to someone else. All right, the next one is grouping to nice numbers. So we saw that before. We called them compatible numbers. Here, we're not so much worried that they're exactly equal to, say, 100, but we're going to look at them and say, oh, they almost are. Okay? So pick me a couple numbers here that seem to be compatible, almost equal to something that would be convenient to work with. Okay, so these two at the end seem like they're very close to equaling 100, right? So we're going to make them together, and we're going to say that's about 100, and we've sort of taken care of these. What else might we group together? You might group the 35 and the 71 together. That would be quite reasonable. You might actually say the 35 and the 55 is actually almost 100 as well. And that would be another way of grouping them that would seem reasonable. I mean, it really is almost 100, 35 and 55. It's 90. That's almost 100, okay? So this would be one possibility, 35 and 71, so another 100. And then the 55 right here, you could either leave it as 55 because it's certainly fine to work with it as 55. You could change it to a 50. That would be a reasonable thing to do too. So you're going to get somewhere in the neighborhood of about 255 here for your answer. So if I get 255 and you estimate it a little bit differently and you get 275, could that still be possible? Sure, that would be reasonable. Because what we're going to be grouping together needs to make sense, but it may not be that we group the exact same things together, and that's okay. Is everybody good on this one? Okay, the next one's one of my favorites. This is one of those things like scratch addition that I told you last time. Scratch addition works really well when you're adding a whole bunch of things together. Compatible numbers works really well when you're adding a whole bunch of things together that are all almost the same value. So it's very specific. This cannot be used all the time. But let's take a look. I've got 442, 538, 457, 554, and 497. They're all close together. Agreed? And they're all approximately what? What's that? 500. They're all approximately 500, right? How many numbers are there? 5. So the approximation here is that these are all about 500. And there are 5 numbers. So what is 500 times 5? 2,500, right? That's really all there is to it. Okay? There's nothing crazy going on, but can you see how this is flat out not useful all the time? Yeah, I mean, this is really specific. But when it works and you see it, it works really, it's fast, super fast. So that's really friendly. All right, we have a couple more. Rounding. Now, rounding in general, we would need to know what we're rounding to. What you're going to see happen in most of the cases on this one is that if you're estimating, nobody's telling you round to what. You get to make that call. So let's do a couple of practice ones. Let's say that we're going to round to the thousands place for practice. And then in a minute here, we'll round to the hundreds. All right, so if I take the number 4,789 and I round it to the thousands place, that has to do with the number 4. It means I'm either going to round it down to 4,000 or up to 5,000. And if you'll remember, the way we make the determination is we look at the number that's directly after the 4, and it's a 7. If that number is 5 and up, we round it up to 5,000. If it's 4 and down, we round it down to 4,000. So on this one, am I going to get 4,000 or 5,000? 5,000. All right, we're going to do the same thing with the next one. The 3. It's either going to round down to 3,000 or up to 4,000. It's not going to become a 2. Occasionally I have somebody think down means that we're going to make that number go down. That's not what we mean. It's either going to go down to 3,000 or up to 4,000. And we make that decision based on the 1 here. And you're right, this will go down to 3,000. And if we add this together, we get 8,000. Let's do the hundreds place, just in case that it's been a little while since you've done this. So now we're going to do it to the hundreds, which means we're looking at the 7. So again, either we're going to go down to 4700 or we're going to go up to 4800, 4700 or 4800. And we make the determination based on this value to the right of it. So this is going to go up or down? Up to what? To the 4,000, and then it's 800, exactly. And then we're going to do the same thing over here. We've got the hundreds place has a 1 in it, and we're looking at the 4 that's directly to the right of it. So this tells us we're going to round down to what? 3,100. And again, we're going to add these two approximations together then, which gives me, in this case, 7,900. Pretty close to the other number, right? And the idea is that if we haven't done anything kind of crazy, they should be close to the same value. Now, if you're asked to do rounding, this does not mean I expect you to round twice. You just pick one of them. You pick the hundreds place, you pick the thousands place, and you just use that. Okay? Last one, using the range. Range is using the idea of what happens in the worst case scenarios. In other words, what happens if I round things down? What happens if I round things up? So let's take a look. So if I took the 370 and I rounded everything down, I'd get 300. The 647, I'd round it down, I'd get 600, right? This is rounding everything down. We're not rounding with rounding rules, we're just rounding it all down. And if I did that, I would get 900. The other option is that I could say, what's the extreme? What happens if I round everything up? Well, then I'd get a 400, and I'd get a 700, right? And what's 400 plus 700? 1,100. So what we say is that my range is 900 to 1,100. This is me telling my daughter as I get up to the register that somewhere in my total I'm going to have between $9 and $11 that I owe the cashier. I turn it into hundreds like pennies, right? 9 and 11, because I don't think I'm going to pay $900 or $1,100. But this is the idea, okay? It's sort of a range of values. It's somewhere between 900 and 1,100 is my answer. All right.